Hello, Prof. Mo here again of chemjoint.com. Let's discuss Lewis acid and bases. What are they? These are subtopic under general acids and bases. One way of defining acids is Lewis acids. Another way of defining bases can be classified as a Lewis base. A Lewis acid accepts electrons, meaning someone has to give him electrons, and that will be the Lewis base. A Lewis base donates electrons. This is different from Arrhenius acid base, different from Bronsted acid base. This is different. So let's look at an example. Let's assume that we have water. That's common, so I'm using it. And then I'm gonna use the H2O to attack a carbon that has a positive charge. Let me put the positive charge on the other side. This species in organic chemistry is called a carbocation. You can see that the C plus here has 6 electrons around it because a bond is 2 electrons. So let me just put the CH3s there so you know those are CH3s, for those who don't know that they are there. Okay, so you have 6 electrons around the carbon. We usually say that carbon wants to be octet, so we can give it 2 more electrons to be octet, meaning to have 8 electrons around it. So we will use the lone pair on water to make the 4th bond around the C+. So when we do that, what we are actually doing is making a bond between the oxygen and the carbon, and I will draw the water molecule here that spent or expended its lone pair or used its lone pair to make a bond, which is what I'm suggesting to be in purple, that arrow right there. That is gonna be joined to the carbon with the 3 CH3s. Okay, so now the carbon has 4 bonds around it, meaning it has 8 electrons around it because each bond is 2 electrons. The formal charge on this carbon will be now 0. Valency of carbon is 4. There's no lone pair on it, but there's 4 bonds. Subtract everything, you're gonna get 0. We started with a positive, now it's 0. For the oxygen though, up there, the formal charge of the oxygen equals to the valency of oxygen minus non-bonding electrons minus number of bonds, which are 3 bonds on the oxygen. That will give you +1. Someone has to show the positive charge on oxygen after this transformation. So when water is in the presence of a carbocation, a carbon which is deficient of 2 electrons with a plus charge on it, you're going to get an alkoxonium ion, we call it, which is shown on here. So here the water is donating the electrons. Those electrons are actually in the new bond. Okay, and because it's donating, we're going to call it a Lewis base. The carbon here is accepting electrons, so we're going to call it a Lewis acid, because Lewis acids are electron pair acceptors. That is the first example. Let's look at another example. Now I can use another type of base. Let me use ammonia in this case, and I'm going to use boron trihydride. Okay, again, the boron is known to be happy with just 6 electrons around it. There's not going to be any charge on it. If you do the calculations, you'll find that boron in this case has a charge of 0. So since it's a sextate, it can take 2 more to be an octet. So we give it the 2 more electrons starting from the lone pair of nitrogen. So ammonia here is gonna play the role of a Lewis base because it's donating the 2 electrons, and the boron is gonna play the role of a Lewis acid. These are reactants. They are reacting to give, that's what this arrow is saying, they're reacting to give you a complex. So the nitrogen used its lone pair to make a bond onto the boron. Remember, these electrons will now be the new bond. A bond is made of 2 electrons. This arrow is just saying these electrons are joining the N and the B, the nitrogen and the boron. Okay, so always when you make products in chemistry, you want to find the formal charges. The formal charge of the boron here will be equal to the valency of boron. I believe it's in main group 3 of the periodic table. Just count the columns, skipping the transition metal elements. You'll find it on main group 3. Then subtract the lone pairs on boron. There is none. Subtract the bonds on boron. There is 4 bonds, 1, 2, 3, 4. The 3 red bonds and the purple one, you get -1. So the boron has a charge of -1. What of the nitrogen? The formal charge on the nitrogen is in main group 5 of the periodic table, valency of 5. It has a valency of 5. There's no lone pair on the nitrogen, yet I have 4 bonds on the nitrogen. I end up with +1, so I have to show positive. So again, nitrogen donated the lone pair to make the new bond, so it's the Lewis base, and then boron trihydride accepted the 2 electrons, is an electron acceptor, so it's the Lewis acid. Let's do another example. Okay, so now let's say that I have a nail polish remover. We call it acetone. Let's say that I have acetone. The oxygen has the lone pair, so we suggest those are the ones to be given out. And then this time I'm going to show a positively charged hydrogen. We call that a proton. Of course, if it's positively charged, it implies that there's no electrons on there. So I can push my arrow suggesting that this lone pair will be donated to the hydrogen. So this will play the role of a Lewis base because it's donating the electrons. This will play the role of a Lewis acid because it's accepting the lone pair of electron. What do we end up with? You end up with a hydrogen sitting on the oxygen that spent its 1 lone pair. You still have a double bond, and then you still have the rest of the structure. Okay, as always, we want to do the formal charges. Let's do that of oxygen. The formal charge of oxygen in this case will be 6 minus 2 non-bonding electrons minus 3, so it will be +1. We need to show a positive here. Hydrogen itself is gonna lose the positive charge because now it has electrons. If you want, you can do the formal charge of hydrogen, valency of 1 minus no lone pair on it minus 1 bond is 0. Okay, proton becomes the Lewis acid, acetone becomes the Lewis base. I hope that helped. See you in another lesson.